The brake system is the unseen superpower of your car, producing more deceleration force than the drivetrain's acceleration force. A standard compact car can generate up to 4.0 gigaseconds of deceleration. A Formula One car can generate up to 6 gigaseconds of braking force, compared to only 2 gigaseconds of acceleration. The first brakes were simple mechanical devices using direct friction. Early systems consisted of a wooden block forced against the wheel's steel rim by a lever. This design was used on horse-drawn carriages and the first steam-powered cars. These systems quickly reached their limits, becoming obsolete with the invention of the pneumatic rubber tire in 1888. The drum brake, patented in 1902, was the first system designed for cars with pneumatic tires. The initial design used a flexible steel band lined with woven asbestos, which tightened around a steel drum to slow the wheel. However, this exposed external band was vulnerable to elements like dirt and water, which drastically reduced its effectiveness. The breakthrough came with the internal shoe design, which moved the friction components inside the drum, protecting the system from contamination. A mechanical cam pushes crescent-shaped friction shoes outward to contact the inner wall of the drum. This converts the vehicle's rotational energy into heat, slowing the wheel. As vehicles became heavier and faster, mechanical actuation through levers and cables became the weakest link. The complex linkages required intricate packaging and were prone to multiple points of wear. This required constant, tedious adjustments to compensate for wear and cable stretching. In 1917, the hydraulic system patented by Malcolm Lockheed overcame the limits of mechanical brakes. The principle is that an input force applied at one point is transmitted equally throughout an incompressible fluid, multiplying the output force. The system uses a master cylinder, brake lines, and wheel cylinders to apply equal force to all four wheels. Even with hydraulic multiplication, stopping heavy, fast-moving cars required significant force. The dominant solution was the vacuum servo, which uses the engine's air intake vacuum and a diaphragm to create a powerful force that boosts the driver's input into the master cylinder. This power assist made its first appearance in 1928. The disc brake concept re-emerged after advances in hydraulics and metallurgy. Disc brakes excel due to superior cooling, better feedback to the driver, and self-cleaning capabilities, resisting water and dirt contamination. The 1955 Citroën DS was the first mass-market car to feature disc brakes. The modern brake system consists of the rotor, caliper, pistons, and pads. There are two primary caliper designs, floating and fixed. A floating caliper uses a single piston to push the inner pad, applying the outer pad as the caliper body slides. A fixed caliper does not move and has pistons on both sides for powerful force application. The final challenge of braking is the physics of a skid. Applying too much force can lock the wheels. The maximum braking force is achieved with 10 to 20% tire slip. A locked wheel leads to increased stopping distance and complete loss of steering control, as sliding friction is less effective than rolling grip. The anti-lock braking system marked the dawn of electronic intelligence in vehicles. Early mechanical anti-skid systems were developed in the 1950s. The first fully electronic anti-skid systems were for the Concorde. Automotive pioneers like Ford, GM, and Bosch introduced the first production electronic systems for cars in the late 1960s and 1970s. ABS works by detecting an impending wheel lockup using a speed sensor. The electronic control unit then commands the hydraulic unit to momentarily reduce brake pressure to that wheel. As the wheel accelerates, pressure is rapidly increased again. This cycle repeats many times per second, maintaining maximum braking force and steering control. The ability to monitor wheel speeds and brake individual wheels unlocked new safety capabilities, evolving ABS into next-generation systems. Electronic stability control uses additional sensors to detect a potential loss of control and can brake individual wheels to keep the vehicle on its intended path. Traction control systems can redirect power to wheels with more grip. The science of friction materials is the unsung hero of braking. Hazardous asbestos has been replaced by sophisticated modern compounds. Common materials include organic, semi-metallic, and ceramic. High-performance cars use carbon-carbon or carbon-ceramic compounds, which offer superior performance, especially at high temperatures. The next frontier is regenerative braking, moving from dissipating energy to recapturing it. The electric motor acts as a generator, converting kinetic energy back into electricity to recharge the battery. This dramatically reduces wear on friction brake components, leading to a sophisticated process of intelligent energy management.